Anything between 70 and 72.
All right, let's see, guys. So I got a nifty question. So 12.5? 11.5? 12.5. Number 70, 71, or 72?
Yes.
All right. I'll do 71 since that's one I can put all up here. All right. You might want to borrow one of these if you need to. There we go. Okay, cool. So let's look at this one. Oh, by the way, guys, chapter 12, or was it the hypothesis testing section? Chapter 10 or whatever?
Everybody, everyone, every person.
Still. There's a worksheet in the back of the book that I said don't worry about. So when you're doing the chi-square stuff, there's another worksheet that you can completely forget about in the back of the book. All right, just do like we did in class. Get the critical chi-square score. Show that it's calculate the chi-squared using the formula, that kind of thing. Just gets to the point. I'm going to show you some stuff today in the calculator, or probably on this one. We're going to do this one the way that I need to see it done, and then we're going to do it again on the calculator, which is not really doing it. It's just feeding the calculator stuff and watching what it spits back at us. But just to show you how it's done in there. And just to show you how to get like p-values and stuff. So this is one about linear regression and correlation. So this is finding the line of best fit, seeing how strong the fit is. So let's see. I can use my calculator. So is there a specific question on this, or what's the trouble? And they got all this business here. For the most part, I agree with these. I like it. This, I disagree with, I think, a couple of answers here. Let's kind of see what happens. If you did this problem, it should... Well, let's see how it comes out. So if you want to play along, let's go ahead and put this data in. The most exciting thing in the world to watch is somebody typing numbers in. So contain yourselves.
I'm so excited. I just can't find it. I'm about to lose control.
Alright. So now, where do we go? Let's see. Blah, blah, blah. What do we do after this? For the line of best fit? Stat? Count. Four. If you wanted to store it, you could. Blah, blah, blah. Alright, so this is what I get. Does that jive with what you got?
Yep.
Okay, cool. Everybody that wants to let me know. All right. Okay. So some other questions. So for example, look at this R. I don't even need. You don't need me to tell you what R has to be. Look at that. Is that good enough?
No.
Hell no. Why? It's very, very close to 0. And it's a very small sample. If the sample was like hundreds of data points, that would actually be good enough to show correlation. Because the larger the sample is, the less stringent the requirement is. Sort of like t-scores. The bigger your sample, the smaller the t-score gets, so the easier it is to pass the test. Same thing with R's. Same exact thing. But that's a damn small sample. So there is no correlation. That's what we would say. There's no evidence of correlation here. Let me stop there for a second. Okay. So some of their questions are kind of silly then. Blah, blah, blah. Is everybody cool with independent variable and dependent variable? Do you guys remember that from... Independent variable is normally which variable in algebra?
X.
X. Because you pick an X, so that's independent of whatever anybody else is. And then the Y depends on your choice. That's why we call it those things. So the independent variable here would be page number. And you're curious about, given a page number, what would the maximum value be on that page? Obviously going in, there should have been no correlation here. Right? It's just kind of as it comes. Let's see, blah, blah, blah. You got the line of best fit. The correlation is significant. No. Significantly bad. But no, it's not significant. Find the estimated maximum values. So right here, I disagree. I think they use the line. Do we trust the line? Will we use the line?
No.
No. So officially, our best guess for any question is the average. That's it. So you would find the average cost, and that's your answer to any damn thing. Because can I use the line to make my normal best guess better? My best guess being the mean. No, I can't use the line because it's crap. Correlation is not there. So I think the book used the line, which is insane. The whole idea is I can only use the line if I've shown evidence of correlation, and we didn't. So I'm not going to use some bogus line that just happens to go through some of my... No, screw that. Blah, 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 blah. Blah, 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 whatever. Suppose there are 200 pages. What do you estimate to be the maximum value for a restaurant listed on page 200? Again, is the least squares line valid for page 200? No. So that's why your answer to part G should be the mean. Don't even use the line. Doesn't make any sense. All right, maybe you guys are with me here. I almost couldn't give you a problem like that on the test. Well, I could, to be honest. I could, but that's just a little weird. I mean, the whole point of getting the line is to be able to use it, right? So if it's no correlation, I can't use it. I like it. Is that part of the question? What was the question there? Did I hit the question, or you just wanted to see one done?
Yeah.
Okay. So if you go to stat tests, let me see. It's been a while since I've done this one. There's the linear regression test. Well, for me, it looks to be F. And if you do this, it'll actually... The reason I didn't do this is I didn't want to really get into the p-value too much. But this is where you actually get calculated p-values for linear regression, right? So instead, I'm just going to give you what the score has to be. I'm not going to worry about the p-value. Let me stop there for a second. Can somebody just look at that p-value? Is that a good p-value? Does it show significant evidence?
No.
Is it going to go off every word I say? No. No. Yeah. What's got to be true about a p-value for it to show evidence? What's got to be true about the p-value for it to show evidence that something's different? It's got to be small, right? You want that tail to be really tiny, meaning your sample is really far away. And this one is, no, it's not far away at all. It's really close to the mean. All right, maybe. So you never have to do what I just did, but I just want to show you it's in there. I mean, the calculator can handle more than the charts can, so why does weird-ass Jeff make you use the charts? So you have more connection with what you're doing. You do this, you have no connection. I've seen students come out of classes where they only use a calculator. They don't understand statistics. They don't have a clue. They just, look at what I made on my calculator. All right, that's nice. All right. You can disagree with that if you want to, but you're wrong. So it'd be bad to be wrong. You can be wrong anytime you want to. It's America. All right, cool. So that's chapter 12, right? And of course, how do I kind of finish this out? How do I get the scatter plot to show up? Where would I go? Oh, how would I get anything? There it is.
Graph, zoom, time.
Yeah, as long as if you're using the same calculator you work, and probably most of these too by now, it should be set up. Mine is turned off, so I got to turn mine back on. List 1, list 2, everything looks good. I'm a square, obviously. So then anytime you put new data in, you've got to hit zoom 9 for zoom stat. And it finds the data. Now, just looking at that, would you say there's correlation there? It's just all over that. That would be a great example to give me if I said, give me an example of R equals 0. I love it. Perfect. All right. I like it. But you can put the y equals in there, but at this point it would have very little. If you took like these guys out, and you can see the negative. That's why the r comes out to be negative something. But it's like that's reaching. That's like reaching for something that's not there. Okay, maybe. So anything else about that kind of problem? Okay. So let's do a chi-square problem, and it is chi. It's not like chai tea, right? It's chi. Again, like Dragon Ball chi. Not kami, chi. All right. So we got goodness of fit problems, and we've got the tests for standard deviations. Tests for single variance is what it's called. So let's just try both. I think, let's do one out of the book. Just do one that I can get. Yeah, okay. I mean, this one's relatively easy. Let's do one with the percentages. I can use this one staring me in the face. Maybe. Blah, 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 blah. 5,000 women. Okay, let's just look at this one. Okay. Blah, 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 blah. So, let's see. This is their actual majors, and this is their expected. This is what they thought it would kind of boil out to be, right? They thought 14% of women would major in arts and humanities. You guys kind of with me?
Yeah.
All right, so when I'm given this kind of thing, when I'm given percentages, what should I figure out first? So there are 5,000, the actual number, right? So to take 14% of 5,000, yeah, 700. So somebody help me out. Keep going. So 8.4% of 5,000. You really just have to multiply by 50. So it'd be 420. All right. Nothing significant there. 13.1% of 5,000. 655. 13 would be 650, right? Is everybody cool with what's happening right now?
Yeah.
Because the problem I skipped there is this one. It said if you roll a die 120 times and you want to check that it's a fair die, well, if you roll a die 120 times and it's fair, how many would you expect to happen for each one of these? How many ones would you expect to have happen? 20. You're going to evenly distribute the 120. So there's no percentages there. It's sort of in the background. There's 1/6 of it, but you guys kind of. But here's the specifically stated percentages. So the first thing you have to do is change it into how many, the number you expect. So 2.6, 130, 18.9, 945. We had 13 once before. 0.4%, 20. 5.8, 290, and 8, 400. Actually, I tell you what. So, to help us out, help me out too, so don't write too much in my book. Let's do something. You don't have to do this, but just so it's easier for me to do up here, let's put these into the list. To the lists here. There you are. All right. If you want to, 700, 420. Because I'm going to show you how to make the calculator do this test for us too. So I might as well put them in here. All right. So here's this is the actual number they saw. Where am I at? So remember, as you're plugging them in, you can kind of, like right here, you could stop and say 145 is supposed to be next to 130. Oh, good. Just so you don't, it always sucks when you're in the next column and you stop one short. Like, oh, shit. Who did I forget? If you've been doing your homework, that must have happened to you at some point, I'm sure, maybe. Now, what do I want to do with those? Besides throw that away, forget about it.
Figure out the difference.
Yeah, so the formula for the chi-square is this observed minus expected over expected. So that's going to be like our z star. So we're going to go ahead and calculate that right now. We got our data staring in the face, and then we're going to look up the, I don't think it says, got to check, I don't think it says what alpha is. So what do we assume alpha to be? 0.05. And you know me, I'm going to tell you what alpha is. So what I need to do here, I can make L3 become L1 minus L2 squared divided by, what was my expected? L1. The only thing you got to be careful about when you're using the calculator is divide by the actual list that has your expected. The E's got to be on the bottom.
Well, so shouldn't it be switched because actual nature should be observed?
That part doesn't matter. Do you guys understand since we're squaring, it doesn't really matter which way this is? Does that make sense? You'll square the negative way. But good point, good point. That's why I didn't even care about that first part, because when you square a difference, it doesn't matter which way you put them. Now, if you don't like that, you can just put them the right way, and you'll get the same thing I'm about to get. Hopefully. So obviously, this idea of using the list in the calculator is nice when you have kind of a longer list to work with. And then what do I want to do with those? Did I put the whole thing in there? I put that whole formula in there, right? Yes. Mm-hmm. So you can kind of, you don't have to do observed minus expected squared and then divide. You can just do it all at once, like I just did. So I'm sorry, you said I want to do what with it? Sum it, right? So I can go to list. If I want to do this old thing, remember this? Math. Sum. Oh, I got to get the hell out of there first. Go away. Get out.
Can't you just do calc?
Yeah, you could. Yeah, when I do that, people freak out. If I do calc 1 var stats on list 3, what's the only thing I care about? The sum. It tells me a lot of other stuff because it doesn't know. It just looks at it like a bunch of data. But I know I just want the sum. So all I care about is this sum is 11 point blah blah blah. Let me stop there for a second. Is everybody still semi with me? I mean, the formula is different, but it's actually the same, to be really honest. It's just like z-scores. It's just like z-star. This is a measure of how far away from 0 I am, how different they were from each other. That's beautiful. So I know that is 11.484, let's say. Oh, that's good, Jeff. You know, 11.484 is our calculated chi. Now let's look up what our critical region chi would be. I think I have a chi-square. Do I have a pencil anymore? Yes. Alright. So if alpha is 0.05, what is it about goodness of fit tests? What am I always fighting against? What is my test trying to show evidence of? So goodness of fit means I have an expected distribution, and then I have what I actually saw. Right? That's the basic idea. So if there was no difference, my chi-square would always come out to be 0. So the test is trying to see, is it different enough from 0? But it can't go both directions like the old z-score, because there's only one way to go from 0, up. Because everything's squared in a chi-squared, hence the square on the chi. So that's why goodness of fit is always a one-tail test. It's always a right-tail test. That's why. Because I'm trying to show that it's far enough away from 0. So you just will never be looking the right way. Here's 0. And I just want to show it's far enough away from 0. So goodness of fit is going to always be a right-tail test. So that's beautiful. So I just have to look at the alpha. Right? And then the degrees of freedom for this is what? How many?
10.
It's 10 degrees of freedom? Okay. So I get 18.307. So then this would have been 18.307. Did we make it far enough away? So that's just like the critical region. This is the critical region. We made it there. 11 point blah, blah, blah. So we didn't make it far enough away. We can't reject that they're the same. So the test didn't say they weren't the same. I love that, right? You love grammar. Didn't say they weren't. You guys with me? So I didn't find evidence that they're not the same. So it looks like they're distributed the way I thought they would be. I didn't find evidence that they weren't. So it looks like the actual majors they got into were close enough to what I expected. They weren't statistically significantly different from each other. Yes, yes, yes. Okay, a little bit of reaction in a few places.
So for your final statement, are you saying we're supporting the hoe, or we're rejecting the hoe?
No,
we
failed to reject the hoe. So we can't say that these aren't the same.
Right.
That's really what you can say.
Does it matter which one you do, whether you say you don't reject the hoe or you don't support the high?
Well, it's funny. The way I just said it kind of captures both. So we can't say they're not the same. Well, the high is they're not the same.
Right.
And we can't support that. And the ho is they are the same. So, but I can't say they're not. I can't reject it.
Previous to doing these, we've always stated a claim.
True,
and
a conclusion.
Reject it or support it.
Exactly.
And on these, it doesn't seem
I just want to make it cleaner, straight to the point. Right? There's not really a claim. It's always the same claim that they're the same. So it's not really, there's no true claim to reference.
Okay.
It's just, I'm testing to see if this fit is good for what I observed. And yes, it looks like the fit is good for what I observed. It looks like what I observed matches what I expected. I like it. Maybe. So again, I really want it to make sense. If there was no difference between the two at all, it would be 0. So if there's only a little bit of difference, then I'm like, well, that's good. So this is just how much difference does there have to be before I can say, no, those aren't the same. That's not right. Right? Like distribution of colors in an M&M packet. My favorite color, I never have enough of my favorite color. Stupid M&M. So then you do a whole test and you show them. Go on YouTube and get buried under all the videos. Okay, all right. I get nothing from you guys to work with. Oh well. Good luck, Jeff. Just do it. Just do stuff. All right. So that's good as a bit. Let's see what it will look like. I got the data in the calculator now. In my list 1 and list 2. So if you go to stats, tests, and you go down far enough, you'll see goodness of fit. Golf. Good old golf. Goodness of fit. So this is the newer RAM. I'm not even sure what it looks like in the older one anymore now. Oh, screw it. I'm not going to put it all in there, am I? No. But it should default to list 1 and list 2 if you have an older version. It won't even say anything probably. Does somebody have that's a newer one, right? You got the same thing I do. Now if you hit, do you have a goodness of fit?
think it's just
Oh.
called chi-squared.
It just says chi-square test. Oh, it does have observed and expected. Oh, that's too bad for you guys. It wants you to put it into a...
Interesting.
Yeah, let's see if I can... Can I reference a list? No. Yeah, you gotta use matrices for that. Oh well. Too bad. It's a good thing you don't have to be able to do this to pass the spots. Degrees of freedom here was 10, right?
Yeah.
So let's see what it says. Let's just do this real quick. So their calculated chi-square is 11.875. I'm not sure why they got something different from us. Let's see what they tell me. Here's the p-value. Right, so we didn't find evidence, right? And that's sure enough, that's big. That's not small, it's big, so that's not evidence. I was kind of hoping, to tell you honestly, I have no idea what the hell this is. That's the center beat. No, I don't have a clue what the hell that is. I think I know what it is, but I can't tell for sure. I don't know. Screw that last thing. I don't have no clue. So some of you guys can't even get this up in your calculator, which is good, which is fine with me, because it doesn't really give you much besides the p-value. I'm not sure why their chi-squared is different. They must have used a modified formula, but oh well. So now you see why the authors of this book like technology a little too much. So now you see why they have questions about p-value on the chi-square stuff, because you get p-values when you do the chi-square stuff in the calculator. But see, if you just did this, if you didn't do the other stuff, you just did this, what connection do you have with what happened? None. You just...
He's this, and it's bigger than that, so no. Yeah.
No. You don't have any connection to what you were doing. Okay. All right. Any other specific questions out of the homework?
12.3, number 24.
All right, so in this problem, it's so that's a weird way to give you this. So X is the amount of money made. I'm sorry, X is the number of endorsements, Y is the amount of money made in millions of dollars. So Y-intercepts occur when X is 0. So right there, you've got everything you need. You know what Y represents. So whatever number you got for the B, for AX plus B, that'll be, and what is that? What does Y represent? The amount of money made, right? When X is 0, when the number of endorsements is 0. So this would be an athlete doing their athlete job, right? But they haven't gotten any endorsements yet. So this is just their what? Their base pay, base salary. Right? And you can all look at the number and go, well, holy shit. They should never complain about anything. Okay, maybe. So Y-intercept, you have to look at what X means and what Y means. Y-intercepts always happen when X is 0. So you say, well, when you have 0 of these, whatever X is, then whatever Y is this much. I mean, that's how you interpret any Y-intercept. It depends on what X and Y represent. So if X was number of months and Y was fish length, the Y-intercept would be, well, you know, before any time has gone by, this is what how long the fish was. Okay. Maybe. I love you guys so much. You guys are a good student never reveals their reactions, Jeff. All right. Inside, you're all like, what the hell? Shit. I don't know. I really don't know. Okay. Yes? Say again? 58? Oh, yeah. Okay, good. Let's see if I can force this guy in there. Alright, that's all we need to be able to see. So 58 really is on the next page. If a loan officer makes 95% of his or her goal, write the linear function that applies, blah, 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 blah. Alright, so where am I at on this chart if I'm at 95%? In between 80 and 100. I like it. So that means this applies. Between 80 and 100, this is what's happening. Right? 81 to 99% right there. So your job, your mission, is to figure out what A and B are. Right? A, X plus B. So what part of this is not going to change? No matter what. 4,000. You're getting 4,000. Even if you're right at 80, you're getting 4,000. But then plus what? What happens here? 125 times, in general, times X, where X is what? Say again?
The additional percentage point.
Good. Additional. So the percentage points above 80. I like it. And then you can plug in for 95 specifically. You just put in there 15 because 95 is 15 additional points above 80. Does that make sense? So first find the equation of the line. 4,000 plus 125x